Thank you. Thanks for the kind introduction, and also particularly for the organizers for putting this exciting program. Over last week, I have learned a lot over the whole week. So in the next about 50 minutes or so, I will talk about some of our work based to model interfacial charge transfer, mostly in the thermochemical reactions, but at the end, probably I can make some connection with electrochemical reactions. So I'm from a chemical engineering department. And some of the, from Oklahoma, some of the idea I'm talking about today, in fact, was generated during my sabbatical last year in Düsseldorf. So I will mention just probably a couple of points at the end. I'm also currently in the transition to another chemical engineering department at Tufts in the Boston area. Since I'm coming from the chemical engineering department, the flavor of the talk will be a little bit different, and hopefully you will see it. Before I run from time, I just want to briefly thank the people who did the work, particularly one of the current postdocs, Shou Tian, and another student, Yan, and two former students, Ting and Wei, and with some experimental colleagues. The first part of the work is supported by the National Science Foundation, and the second part is mostly focused on work from Department of Energy over the last almost 10 years now. So about 11 years ago, so I came from a surface science community, in fact, and the material science, surface science community. About 11 years ago, when I joined the chemical engineering department, I need to find a topic to start with. At that time, one of the topic is biomass conversion. And the whole idea was using biomass as a distributed feedstock, because the current chemical industry is normally operated at high temperature, high pressure, centralized plants, and that also requires a large-scale operation and a large capital investment. The idea is to switch to some more distributed feedstock, could be biomass, could be air or water. Now you operate into a smaller scale plant at a lower temperature, lower pressure, and hopefully also at a smaller scale, only for a distributed, only for a local community, and with lower chemical investment. To drive the reactions, of course, you need some external stimuli because you want to operate at low temperature, low pressures. Since at that time we are focused on biomass, and then water cannot be avoided because you have a lot of water in biomass. To separate the molecular from water and then do conversion is very challenging, so it's more ideal to do the reaction in water. So that's essentially where I came to this community to study how solvents affect the reactions. The general picture, at least in the catalytic community, the idea is that you have, let's say, for a simple A to B reaction, you have a gas-phase reaction get dissolved into liquid, and then adsorb at the solid-liquid interface and go through an activation barrier and end up with the product and eventually dissolve into the solvent and then leave to the gas phase. Now your surface species, in this case, for example, A, and also your transition state here probably will experience the solvent differently, so that your apparent barrier will be different by doing the reaction in different solvents. Of course, the solvent can also directly participate in the reactions, like has been already talked about several times in this symposium about proton shuttlings. Over the last about 10 years or so, we have started many different reactions, and we wrote a few review papers over the last 5 years. A lot of knowledge has already been generated many years ago. In fact, as I mentioned, I came from a surface science community. People have done this kind of ice, monolayer water, monolayer ice on different metals. The trick part is the dynamics. This is from the group in Ulm, showing the dynamics of the water and also the variation of work function. I think Jörg also mentioned in his talk. And then water can also participate in the reaction itself, for example, in acid reactions, or in this case, oxidation of alcohol. And it has also been shown that the water is responsive to the external perturbation. In this case, electropotential is from Xiamen University quite a few years ago. So that's what we know at that time. So we say, okay, leverage what we learned from the literature, what can we do? So in the talk, I'm going to focus on 3 examples. In fact, the first example is on the lithium-sulfur battery. I'll try to show the computational hydrogenation model. In fact, it works pretty well for that one. And then I will show you talk about some acid-catalyzed reactions in which you form a very charge separation from a large dipole at the transition state, and then you need your solvent to stabilize this charge separation at the transition state. And then we can treat it with the implicit solvent model. And in the last part, I will talk about dynamics and charge transfer, and particularly how the reaction kinetics, the hydrogenation, depends on the configuration of the first layer of water. In the first case, I'm looking at the lithium-sulfur battery. During the discharge, the lithium will leave the anode and go to the cathode, react with the sulfur, which is the cathode material. At the end of the discharge, you form a lithium sulfide. And when you charge the battery, the lithium sulfide, the lithium has to be, of course, reduced back to lithium, and the sulfur back to sulfur-8. This is a 16-electron process, and it has many challenges. The good thing is it has high capacity and energy density, but it also has many challenges here. I will just, in the next couple of slides, focus on one is the shuttling of the polysulfide, the other one, the slow kinetics. So during the discharge process, the lithium, which is indicated by the small blue dots, will react with the sulfur. And at a different level of discharge, you form this different lithium polysulfide, lithium-2, sulfur-8, sulfur-6, sulfur-4, sulfur-2, sulfur. So, and those lithium polysulfides, they are very polar, and the electrolyte normally also polar oxygenates, like ethylene carbonate. So the lithium polysulfide can get dissolved into the electrolyte, and they can even transfer from your cathode to anode, so eventually your sulfur is lost at the cathode side, and because they are moved to the anode. And also sulfur is insulating. It will also hurt the overall performance. To stabilize lithium polysulfide at the interface, I just go very briefly to it. People have proposed to use carbon material like graphene. What the ratio is, in fact, what really matters is the impurities like oxygen and this carboxylic group, or nitrogen, or some oxygen, including molecules, in this case, just the surfactant and tritone. They can stabilize the polysulfide, not the graphene itself, because as I mentioned, the lithium polysulfide is very polar, so you need something polar to stabilize it, and in this case, the oxygen impurities. How about the kinetics? Which means how you really try to activate the lithium-sulfur bond, particularly during the charging process. You have to reduce your lithium cation back to lithium. And in this case, we are using atomically dispersed metal embedded into carbon material. This work done by Wang now, who is a postdoc at the Naval Research Lab. The reason we use this atomically dispersed metal, one is reduce the cost, and the other one is also because in the battery, you want to reduce the weight as well. So we don't want to have a lot of metal. Instead, we want to use a single atom size. So for the first part, we just screen about 20 different metals and look at how they stabilize this lithium sulfide. So I plot the binding energy. In fact, it's just absorption energy of different lithium polysulfide, lithium-2, sulfur-8, sulfur-2, sulfur, onto different metals. More negative just means more stable absorption. Immediately, you can see that some metal does very well. For example, in this case, titanium, vanadium, and in this case, like niobium, molybdenum. So we definitely have some metal to choose. Then how about the thermodynamics? So we simplify the reaction into, it's a 16-electron process, but we simplify it to a 2-electron process. So in the first step, the lithium-2 sulfur just becomes lithium-sulfur, and generating a lithium and an electron, and then this lithium sulfide will be further oxidized from lithium plus. Now you can calculate the reaction energy, the delta G of each reaction, and you choose the most difficult one, and you can convert it to the potential. And if you reference to the open circuit potential of lithium-sulfur battery, in this case we're using 2.2 volt in this case, you can get essentially the overall potential, which is how much additional energy you need to drive this reaction. The overall potential energy is plotted at the y-axis, and here there's some descriptor we identified, which is some relative stability between some surface species, which is not important in this particular talk. We notice there is a group of metal has exhibit lower overall potential, particularly the same metal I just mentioned, molybdenum, vanadium, niobium, titanium. Tin and germanium also does it pretty well, but it does stabilize the polysulfide as well as the other ones, so we exclude tin and germanium in this discussion. So I didn't mention that in this case, when we calculate the chemical potential of the lithium plus and electron, we're essentially using just the lithium in the bulk metal. So it's the same analogy like in the CHE using H2, half H2 to model the hydrogen chemical potential. So how about the electrolyte? In this case, we did the microsolvation. We introduced two different, two electrolyte molecular. This is ethylene carbonate. Because they have oxygen, each oxygen will form a strong bond with the lithium. We did the same calculation of the overall potential and plotted here. Even though the absolute value changes, but the general trend is there. So again, there are some metals did better than others. So this is purely thermodynamics. So how about the kinetics? How I can drive the dissociation of lithium-sulfur bond, which is shown here. So I have a lithium-2-sulfur. I break one of the bond. I just show the trajectory of the lithium will diffuse to graphene phase. In the two figures, I'm just plotting the activation barrier for this particular process. On different metals, in figure B, I'm showing some descriptor at the bottom, which is, again, some relative stability of some intermediate species. But generally speaking, we can, again, identify a group metal. They also have a lower kinetic barrier for lithium-sulfur bond activation. Again, it's something like titanium, vanadium, and molybdenum, niobium. So we did this work, in fact, during the pandemic time. We have plenty of time to do something, but we never published that because the model is just so simplified. We don't really have, we're just doing a constant charge approximation without doing any electropotential into it. We treat the electrolyte in a very simplified way. Even the active site we treat was very simplified. So we only get it published recently until we have some experiments to verify it. So let me just remind you, so from this calculation, if we can essentially have three different groups. One group is on the corner here. They have very good thermodynamics for the reaction and also good kinetics. They can also stabilize the lithium polysulfide. The second group is somewhere in the middle, probably centered by iron, and there's a third group of metal. They're not doing as good as the other two, which is like nickel. Experimentally, I'll just go very briefly on that. It's done by Zhao Yangfan's group at Arizona State. We did a cyclotometry, identify a couple of peaks, the redox peaks, and then plot that against the overpotential. You can essentially the Tafel plot. You can get the Tafel slope. And you can also measure the cyclostability. The bottom line is, at the end of the day, niobium is better than iron, and iron is better than nickel, and nickel is better than the one without the transition metal. It's exactly the same trend predicted from the computation. So it's kind of a little bit surprising that this simplified model, simplified calculation can indeed predict the active centers. But I think probably the reason the reason why it works is really because first, we'll compare different metals. The solvation effect probably cancel out between different metals. That's one thing. And second, I think it's also why the CHE model works here is that the reaction is very endothermic during the charging process. So your activation barrier is very much the same as your reaction energy. That's essentially similar to what Jens Noskov did at the very beginning of CHE model. The assumption is the protonation of a reactant, the barrier is very much the same as the reaction energy. So you can use just the thermodynamics to predict the kinetics and then screen different metals. I think here that's probably the same reasons. Okay, that's the first example. In the second one, I'm talking about another topic, which is acid-catalyzed reactions. In this case, suppose I have acid. In this case, it's just like a proton here. And now I have a hydrocarbons. The first step of the reaction is the protonation. So the proton will go to the hydrocarbon, and that will drive a crack of the CC bond or CO bond, depending on which reaction we're talking about. So but the point is, when you do the protonation, you form a very positive charged transition state, and the electron will remain at your active site. So you form a dipole at your transition state. And this charge separation is generally thermodynamically unfavorable. So how to stabilize the dipole become a concern. And we have studied several different reactions like cracking reaction, isomerization, dehydration, isolation. All of them, in fact, involve a similar transition state. So I use one example to show it, which is the dehydration. So here, the top panel just showing a typical acid site here, and then I have alcohol. The top panel is just in the vapor phase, in the gas phase. So the molecule will dissolve on the surface, and then go through a transition state. Presumably, the rate is limited by the CO bond cleavage. So you have this positive charged transition state, and then you break the CO bond, and eventually the proton has to go back to active site to recover to close the cycle. Now you put the whole reaction step, but immerse them into a solvent, which is the bottom panel. Now, as I mentioned at the very beginning, that your surface species and your transition states probably will experience the solvent differently, and then the activation barrier probably will be different. What I meant is, for example, when you form a positive charged transition state, let's suppose you're doing in water, and the water has a dipole. The dipole has to reorientate to respond to the formation of this dipole at the transition state. And that probably depends on the nature of the transition state. For example, how large the interfacial charge transfer is, and also depends on solvent, how they can respond to it. So this is just a summary of the experimental results. It's from Cassie Chen's group in Toronto. One of his students, Junfeng, he did a lot of work. He looked at 5 different reactants, which is shown here, in 9 different solvents, and measured the activation energy, which is here. So that's a lot of work, I can tell. The question is, can we predict, because this is really a lot of work, can we predict even the activation barrier without doing such immense work? So here we plot the delta G. This is the activation that another delta comes from. You compare the liquid phase with the gas phase. That's another delta comes from. The question is whether we can, this is the experimental merit value. The question is whether we can predict it. And in fact, it can be predicted with a quite simple reaction, quite simple equation. In one case, which is the delta of the methanol adsorption, which is just a problem molecular, which is not really the case in this particular talk. But this tells on the adsorption side. What really matters is the second term is how the transition state is stabilized. You can see that the alpha, it should be in the unit of kilojoule per mole, and times some dielectric form written in ensemble functions, which shows how the continuum dielectric constant interact with the dipole that it is surrounding. So somehow it works. Now with all the data, with the 5 different solvents, 5 different reactants, 9 different solvents, we can put all the data and show that experimental results kind of agree with these predictions. Of course, in this case, the alpha is a fitting parameter. The alpha is just from regression, which is shown here. The alpha value, in fact, changed quite a bit from somewhere minus 26 to somewhere 11. So the alpha essentially tells you how it is how the activation barrier is sensitive to the dielectric screening. So we try to explain the physical meaning of the alpha. So this is the postdoc Shou Tian. He built this acid site, which is amber list 15, which is essentially sulfonate functionalized hydrocarbon backbone. We can calculate the initial state, which is one of the alcohol used in experiments, cyclohexanol. It adsorbs at the acid site, so you have some polarization. And this is a transition state after the proton is transferred to the molecular. On the right side, we plot essentially the charge density difference along the z direction. Now you can calculate the charge density multiplied by the distance. You get the dipole and dipole moment, and then you can integrate across the whole z direction. You get the overall dipole moment. As I mentioned already, that as you notice in the transition state, which is the red curve, after protonation, you see a much larger or much pronounced charge transfer. And in this case, the negative number means just electron loose. So after proton transfer to the molecular, the positive charge is really localized on the surface species. You can do the exact same calculations for two other different alcohol. This is dimethyl-butanol, and the other one is phenol estanol. In fact, that's the 3 molecular we tried. What I'm showing you here is the correlation between the alpha value I showed in the previous slide, which is from regression of the experimental data, and the x-axis is the DFT calculated dipole moment at the transition state of the 3 different alcohols. And indeed, the alpha value have a very linear correlation with the dipole moment. That in fact makes a lot of sense. That depends on the strength of the dipole at the transition state. If the dipole is large or the charge transfer is large, then it's more sensitive to dielectric screening, and vice versa. I show 3 different figures just by changing the probing molecule from methanol to pyridine or acetonitrile, but the general trend is the same. The key concept is here is how to stabilize this transient dipole for acid-catalyzed reactions. One thing we are still working on is, because the question can be asked, is how about we just introduce implicit solvent model by changing the dielectric constant and plot activation barrier as a function of the dielectric constant. We are working on that. We don't really get exactly linear trend as we are expecting. But at least this correlation suggests that the dipole moment at the transition state definitely matters. In the third example, I'm going to focus on the proton dynamics has already been talked about several times in this symposium, and how the explicit solvent has to be used to deal with the proton dynamics. So in this case, we did some experiments were done by my experimental colleague at OU. So we started with the furfural. It's a biomass molecular. You can generate pretty easily from biomass. You have this conjugation between the CO double bond and CC double bond. You can do the CO hydrogenation. You can get this molecular, so-called furfuryl alcohol. You could also do the CC hydrogenation, get this one. Now we do the same reaction. It's on palladium supported on gamma alumina. If you do the same reaction, but one in water and the other one in sulfur, you notice the conversion, which the black bar, increased a lot by a factor of 3. Meanwhile, the selectivity to this product, which is essentially the CO bond hydrogenation, is also being promoted. So somehow the presence of water not only increased conversion, but also increased selectively the CO bond hydrogenation. So this work was done by 6 or 7 years ago now. So at that time, we did ab initio MD simulations with the palladium surface with about 60 water. We run, that's probably the best at that time we can do, about 20 picosecond. We position the furfural at different locations, but eventually we only use the data of the furfural at the interface. So after run that, we get a lot of trajectories. And then what we did is just pick one of them and crawl it down to 0K, basically optimize it, and then do NEB. That's essentially what we did at that time, which is shown here. The CO hydrogenation has 2 steps. First hydrogen goes to oxygen, and the second hydrogenation goes to the carbon. That's finished the CO double bond hydrogenation. We compare, in this case, the dashed line represents the calculation without water. So this is the first hydrogenation, and this is the second hydrogenation, and the 46 and 34 is just the energy of the transition state with respect to the reference here. Now, in this case, I introduced water, but in this case, water doesn't participate in the reaction directly. They are purely just a spectator. But in this case, already, they can stabilize the products, which is, in fact, understandable. Because initially, this is the aldehyde, but after hydrogenation, you form OH. The OH have a stronger interaction with the water, so the water stabilizes the hydrogenation products. So here we just shown that the reaction path is the hydrogen, which is coming from the surface, eventually attacks the aldehyde oxygen atoms in the direct path. So this is purely driven by thermodynamic stabilization. But as already been mentioned several times in the symposium, the water can do much more than that. So in this case, suppose I have water in the first solvation shell. The water can pick up the proton or the hydrogen from the surface and transfer its own proton to the oxygen and complete the CO hydrogenation with the second carbon hydrogenation. Now we introduce this mechanism, we notice the barrier for the first hydrogenation is further reduced. This is by about another 10 kilojoule per mole. And if you compare these 2 paths, what happens is in the previous one, we have the hydrogen directly attack oxygen, while in the second case, the hydrogen goes to water and then transfers its own proton, which transfers its own proton to oxygen. That essentially means different path. The carbon hydrogenation is not very much affected by the presence of water because the carbon here is more hydrophobic. It doesn't have a hydrogen bonding network, so the proton cannot be shuttled to the carbon. So only the oxygen hydrogenation is promoted. And in fact, not only the first shell water, even any water at the interface can do the job. The water can pick up the hydrogen and transfer the proton. And here we just pick up another water, and now we show that the barrier can be further reduced. If you look at the charge transfer, if you look at the transition state and do a charge transfer analysis, you can show that very much about a positive charge associated on the H3O. So it's more like a hydronium iron mechanism. So how to support or validate this computation? In fact, one thing came out of this computation is that we can predict the reaction order should be different. Because if without water, the highest barrier in fact comes from the first step. While after hydrogenation, because the first step, the oxygen hydrogenation is very largely enhanced, the reaction is limited by the second step. That will cause a different dependence on the partial pressure of hydrogen. And that's indeed exactly what happens in experiments. If you measure the rate plot in a log-log plot at the partial pressure of hydrogen, you can see in one case, in the sulfur hexane, the reaction about half order, while in water it's about first order. Without going into details, essentially what you could do is write down the Lamb-Henshaw reaction rate equations. You can show that this change of reaction order is indeed caused by the change of the rate determining step, which is shown already in our simulations that without water, the reaction is limited by the first hydrogenation. It's corresponding to a half-order reaction, while if you go to the water, the first hydrogenation is promoted, and now the reaction is limited by the second hydrogenation. It will create a second order, a first-order reaction because the second step hydrogenation. So in a simple picture, we show that for the first oxygen hydrogenation, the reaction is driven by the water-mediated process, while the second hydrogenation of the carbon, let's go back again, the second hydrogenation of the carbon is still comes from a surface process. This is what we did already quite a while ago, but then a lot of questions come out because we did just one snapshot calculation. We don't take into account how the configuration or the dynamics of the water may change in the simulations. So how the reaction kinetics depends on the dynamics of the water in this case. So ideally, if I can look at a broad distribution water, I can sample that, and then I can look at the free energy for the different hydrogenation paths. So, but instead, what we did next is just a simplified way. It just, instead of picking just one snapshot, we just take much more snapshots and see how much the dependence of the kinetic barrier depends on the configurations. It's done by team. So we built two different cells. One is we have vacuum. We don't have a vacuum. The whole cell is filled by water. In the other case, we keep a vacuum here simply just to get the vacuum level so we can calculate work function. We choose about 10 different configurations, and here we show that for different, represent each different configuration, and here is activation barrier. So as you can see, the activation barrier is changed from almost 0 to somewhere about 80 kilojoule per mole. So in our initial work, we probably choose a configuration somewhere here. So if at that time we choose a configuration somewhere here, probably never publish the first paper because we don't even know where the barrier is. So how to address that? First, how to explain why it's dependent on that. In fact, it can be quite easy to explain that. Because we are looking at this hydrogen transfer process, we can look at the collective variables. One is the distance between water and the hydrogen. The other one, the distance between water and the aldehyde, because this is where the hydrogen has to go through the whole path. You can immediately show that if you increase the CV1, which is this hydrogen bond between aldehyde and the water, the barrier is increased dramatically. A little bit of change of the hydrogen bond length will increase the barrier. And similarly, if you increase this distance a little bit, and then the barrier also increased dramatically. So a very small change of the local water configuration can affect your kinetics, which I will show you in another example. So we can understand that. So the idea then is we should probably run, we probably should fit all our data from our MD simulations and then fit into a machine learning model. Then we can do umbrella sampling to get some free energies. To generate a data set, so we don't have a data for that yet, but to generate a data set, what we did is the following. So the red curve is just NEB calculation from one of the snapshots I chose in the previous slide. And then for each image, I fixed the transition state, but now we allow the water to move in the MD simulation. So essentially, it's a constant MD. And the black dot just represents the mean value during the MD simulation. And the arrow bar, in fact, not arrow bar, it's just the variation of the total energy at each fixed image. As you can see that the variation is pretty big, as big as the barrier. The barrier is somewhere around maybe 0.7, 0.6 EV for the red curve here, 0.6. The variation is, in fact, beyond that, like 1 EV. That makes us to think whether it's really the hydrogen has to follow the reaction coordinates to attack the oxygen, or the hydrogen has just to wait until the water to evolve to certain snapshots that is more kinetically favorable for the hydrogen reaction to happen. Of course, it's a collective motion. So right now, we have a lot of snapshots, energy and force. We try to fit all of them into a machine learning model, and then we try to get the free energy for the hydrogenation reactions. Hopefully next time when I'm here, I can talk more about that. I can skip this one. So I mentioned about, in this case, so I said probably the water has a very broad distribution, but at the end of the day, probably some distribution are just more active than others, because the water is dynamically evolved from one to the other. And also I mentioned that a small change of the water configuration at the interface will determine your whole kinetics. So the question is whether I have a way to somehow constrain my water distribution to a narrow one, so I can favor its particular configurations so that I can promote the reaction kinetics. And that's the one I'm going to talk about in the next probably 10 minutes. So the idea is the following. So we are using different reaction in this case. It's NO2 reduction, thermal reaction again. NO2, it's just a nitrite reduction to N2 and ammonia. It's the same palladium catalyst supported on silica. The idea is if I introduce some confinement, in this case the polymer. So if I can introduce the polymer, the polymer is grown on the oxide and support, not on the catalyst active side. If the polymer somehow will surround my particles, then my water will be trapped at the interface, and how the water will behave differently within its confinement compared to the water in the previous case, which is more like a free water. So without going to the details of the reaction kinetics, this is the experiment done by Jimmy Faria at the University of Trinity. So we can essentially write down the whole elementary steps, and then we can derive the Lamian-Henshaw reaction rate and predict which one. And we can essentially estimate the rate depending on which one is the rate determining step. They also measure isotopic experiments. But I want to go to the details. I don't want to do calculations instead. So in this case, we need the NO2 minus absorbed on the surface, and then it forms NO. And the NO will do hydrogenation, which the first hydrogen comes to nitrogen, and second one comes to the oxygen, and then you cleave the NO bond and form NH, and NH will be hydrogenated sequentially and eventually form ammonia. So that's the reaction mechanism we published a few years ago now. The rate limiting step, which is the one that has the highest barrier, is normally the first couple of steps. In fact, it's very difficult for us also for experiment to distinguish which one is exactly rate determining step. So we think probably both has a large degree of rate control, so-called. And definitely what the presence of water helps the hydrogenation through the same shuttling mechanism, which means the hydrogen from here can go to water nearby, and then the water can transfer the proton to the nitrogen, and that reduces the barrier shown here. So in this case, there's no particular confinement. It's the same thing as we did in before. We just put a water layer on top of that and study the kinetics with NEB. Experimental now, they grow this polymer on top of the silica. This is the pan-nippon polymer. This pan-nippon has the thermal responses. So at low temperature, below the critical temperature about 32 Celsius degree, the polymer will swell in water. And in this case, the polymer length is about 70 nanometers, so it's pretty long. When you increase the temperature, the polymer will collapse. The polymer in this case want to interact with each other. They will collapse from a condensed layer on the surface. So now the idea is if we can measure kinetics within these two different regimes, when the polymer are swollen in the water or when the polymer collapse, and see how the kinetics change. And here is the experiments. Experimental results. On the left side, it's no polymer. You can get the barrier about 36 kilojoules per mole, apparent barrier from experiments. When the polymer collapses, the barrier is very much the same as when there's no polymer. While when the polymer swells into water, the barrier is much reduced to a level about 11 kilojoules per mole. So we can further decompose it. Looking at both the delta H and delta S, as you'll see that when the temperature is 22 to 32, which is when the polymers swell, the activation barrier reduces from 30 to about 11. And meanwhile, my entropy also reduced a lot at my transition state. So there's a compensation. There's a compensation there. So when you stabilize your transition state, you also lose a lot of entropy at your transition state, which is not that surprising. But the real question is why cause this reduction of the activation enthalpy and also the activation of entropy. What we did here is we tried to model this metal-water polymer interface which is, of course, impossible for DFT. So what we did is the following. So we picked just a palladium surface. Instead, put a polymer, which is 70 nanometer long. We just put 2 monomer into the water, and then run MD, and see how the presence of these 2 monomer will affect the water configuration and also the reaction thermodynamics and kinetics. So the first question we want to answer is whether the presence of water or the presence of the polymer may or may not affect the hydrogen stability on the surface, because it's the hydrogenation reactions. If I can affect my chemical potential of hydrogen, then my kinetics will be different. It's very difficult to evaluate the hydrogen stability, so what we instead did is we look at the bond length, the vertical bond length of the hydrogen from the metal surface. This is from MD simulation. And then we can do the Fourier transform of that, so we get the out-plane vibration of the hydrogen on palladium. So the vibrational frequency is somewhere around 30 terahertz. And in fact, back to 70s, 80s, people in surface science community has already measured that for hydrogen vertical displacement on palladium is on about 30 terahertz. So the agreement seems to be pretty good. And also the presence of water and the presence of polymer doesn't really affect my hydrogen absorption, at least from the frequency argument. There's a small shift here, but we are not very sure. That's probably just from the uncertainty in the calculations. So another thing we did is we look at the water distribution. I mentioned we put 2 monomers, which is in fact here. We put a monomer somewhere here, and the other monomer is a little bit above the surface. So the results probably also depend on where the monomer we put. It's the palladium surface. We have 2 NO molecular, and the rest is water. So now we plot the water profile. It's the vertical position. The 0 is just palladium surface. The purple curve shows here, this is the water peak when there is a polymer or monomers. You can compare with the shaded area, which is just water without the presence of any monomers. We see there's a small downshift by probably about 0.1 angstrom, because when you have the polymer there, the polymer somehow pressed water to the surface. It's very small, just by 0.1 angstrom. You can again look at some water in the interface. You look at oxygen vertical displacement as a function of time. And then the purple one is the one with the monomer, and the green one is there's no monomer, just water. You see again, there's the overall average is a little bit about 0.1 angstrom closer to the surface. And also, if you look at the vibrational, the whole dynamics amplitude, when there's a monomer nearby, the whole dynamics of the water is also largely suppressed. So what happens is we put these polymers is right between the first layer and the second layer of water. So the first layer of water now is more bound to the surface than putting it this way. That's what essentially the simulation is showing. Yeah, good. I'm almost there. So there are some kind of constraint of water to the surface. Now we can give you a hand-waving answer first, which is the argument is the following. So if I want to know hydrogenation, hydrogen goes to water, and then the proton goes to nitrogen. So now if I introduce this polymer, what may happen is now I have this water more approaching to the surface. So now by changing a little bit this distance and a little bit this distance, I can promote my kinetics, as I showed already before in the sulfur hydrogenation example. And this change could be very small, probably just by 0.1 angstrom. And because they are close to the surface, the whole transition state is more bound, so the entropy is lost, even though enthalpically it's promoted. Whether it's really true or not, we don't know. But now I'll give you another piece of information, which some result we did recently. We picked exactly the same system here with water, but no polymer, just water and NO and palladium. That was during my time in Düsseldorf. So at that time, they used the neon layer as a counter electrode. In this case, I just use the neon layer as a physical barrier. And then what I'm going to do is I introduce a flat neon sheet, and then I push it down as like a piston to compress water, step by step, to say, we start with the same water structure, so the water configuration don't change that dramatically. It's just some local distance change, which is shown here. So here the x-axis is just more or less the compression you can imagine. So here initially, this is the initial height of the oxygen at further from the surface. You compress it. So this is the oxygen displacement. which is oxygen on the very far away water. So its transition from left to right is just compression. And then the left axis is just the first hydrogenation activation barrier. And then the y-axis shows the distance between the OH, which is this water, and this hydrogen distance. And the other one is the red one is the NH, which is the nitrogen and this hydrogen. So where the hydrogen goes and where the hydrogen will go ends. Right? We plot these two distances. So with a little bit compression, as shown here, that I can see that my OH distance with this one reduced a little bit, somewhere on the order about 0.1 angstrom. And similarly for the hydrogen-nitrogen distance, also compressed a little bit. As a consequence, the barrier reduced a little bit. What's interesting is when you further compress, the barrier just goes so high. Right now, our understanding is when you compress it, this water becomes so bound to the surface, then it becomes so difficult to pick up the hydrogen and then transfer it, just because the water is so too much stabilized. We are still looking at analyzing the data, but at least this is compared to the previous slides showing the compression. We have this kind of argument that just change the water configuration by a small amount, 0.1 angstrom, your kinetics barrier probably already changed dramatically. So since this is on electrochemistry, I cannot avoid just one slice of electrochemistry we are doing. This is a simple reaction with this molecular quadrisaline. The idea is if you apply potential, particularly on the more positive potentials, you can withdraw electrons from the molecular so that the molecular become a radical, and then the CC bond breaks, and eventually it's transferred to NBD. Of course, the whole argument before is using this NBD molecular as an energy storage molecular to store solar energy. So under light, you convert NBD to QC, and then using electrochemistry to convert it back. And in this process, it's very isothermic to release. You can release the heat to the local environment. So that's the argument. Then you can choose different catalysts. So the current understanding is limited by the first step, which is to withdraw electron from the QC molecular. Looks like from the HOMO. So in the following, we did a very quick test without doing any fancy explicit talking about the dynamics of water. What we did is simply just implicit solvent model. We have the graphene in this case and the molecular, and then we simply tune the number of electrons in the graphene layer using the implicit solvent model on top to compensate. As you expect, if you lower the Fermi level here from minus 4.3 and further lowered, Fermi level goes down and down, so you're moving more positive potentials, your barrier also drops. That's because because the Fermi level is going down, you withdraw electrons from the molecular, then the bond can break. And then we also plot the activation barrier as a function of the Fermi level change. We see somehow it's a linear change, but we are still in the early stage of analysis data. I put it here just to satisfy the audience that we are also working on electrochemistries. But in fact, we notice right now in the catalysis community, there are a lot of discussion that some reactions, even though it's a thermal reaction, but you can still manipulate the thermal reaction using open circuit conditions. So you just simply change the Fermi level of your catalyst. You can already do the reactions without a real redox chemistry. And there are a lot of results shown recently. But we're also working on that, but I won't go to details of that. So that's one summary. So suppose I have active size. Now, when I have a molecular absorption or some reaction happens from some transition state, there might be some dipole formation at the active size. This dipole formation is very sensitive to the local environment. So the local solvation, particularly in the first solvation shell, we provide dielectric screening and proton shuttling, and this is very configuration dependent. And then at another layer of complexity, you can further tune this solvation by introduce some perturbation. In this case, we are using a pretty big polymers, but you can imagine that, in fact, you can even do apply electropotential or using light. In fact, a lot of our work in the previous years, we're working on plasmonic analysis. We also show that, in fact, solvent also play a role. So with that, I want to thank people who did the work again, and thanks for you to stay until Friday for this talk. Thank you very much.